So when working with infinite dimensional vector spaces, it's often useful to use a different notation. Rather than writing V bar, I'm going to write this ket vector V here. All right? When I have an inner product, I'm going to put a bra vector, which is like backwards, like that. So the inner product is written like this. Okay? Bra ket. Dirac was a funny guy. Anyway, so this is going to be our inner product. The way in which the bra is related to the ket is what defines the inner product. Okay? So as an example for our standard inner product, if I've got that as my ket vector, my bra vector would be that. All right? Now, if I'm using complex numbers, then I'll also have to do that little complex conjugate that we looked at. So for our purposes in finite dimensional vector spaces, the bra is just the complex conjugate transpose of the ket. All right? Now, part of the reason that this notation is better when working with infinite dimensional vector spaces is that it makes for a clearer definition of the adjoint. Remember we had the adjoint, all right, or the transpose that we looked at earlier, where we just switch the rows and the columns. For a general inner product, that is a general, product of two vectors satisfying our three properties: linearity, symmetric, positivity, symmetry, positivity. All right, we're going to define for a given operator A. So think about what's happening here. I've got ket vector V. I act on it with operator A. That gives me another ket vector. And then I do the inner product with U. Okay? Sometimes people say that A has been sandwiched between those two vectors, the ket and the bra. We define the adjoint, A dagger, as the operator that produces the same effect that A does when acting on V, but it produces that effect when acting on U. All right? So I could say A dagger forms the operation of A acting backwards. All right? It's like A dagger is the operator that does the same thing as A would do acting backwards. It takes a minute to digest what's going on here. So let's do an example with the standard inner product. So I'm just going to make something up. Okay? So this would be my U, my A, my V. All right. So what we got? All right, we've got 18 plus 1. We've got 37. All right, so this would give me 19 minus 74, right, which is negative 55, maybe? All right? Now, I said that A dagger is the operator that produces the same result here, but when acting backwards. All right, I can see that from two different perspectives here. We already know that our adjoint was the transpose. So let's just use the transpose and see what would happen. If I had the transpose, or I'm going to write this dagger like that, for the standard inner product, the difference is that you have to do the complex conjugates. And I'm not going to use complex numbers here, so it's not going to matter. But that is true in general. Okay? So I would have a dagger and then acting on 1, negative 2. Right? Because that's what this says. A dagger acting on ket U. All right? So what would that be? Well, I'd have 3, 5, 1, 7, acting on 1, negative 2. And that's going to give 3 minus 10, and then 1 minus 14. All right? You might say, oh, that's not negative 55. And that's right, it's not. That's because that's only this part. Now I have to do the dagger of that and act on 6, 1. Right? So I would get negative 42 minus 13, which indeed is negative 55. All right? Now, one thing that's kind of interesting here is that with the standard inner product, I can see that this is really A acting backwards. Why it's the transpose, looking at it from a different perspective. What if instead of multiplying here, I multiply here? All right? And you could think of that quite obviously as A acting backwards. All right, let's see what it gives. So I would get 3 minus 10, negative 7. And then I would get 1 minus 14. You guys see that? All right, so from perspective, that's why the transpose gives the adjoint.